Hey folks, we're on to section 3.4 here, relational algebra. Now I'm going to be honest here, this is probably one of the worst sections, super heavy, very mathematical, tons of technical terms. I mean, maybe not even mathematical, but lots of technical terms, lots of definitions, lots of new characters and language that we're going to use. And we're not really going to do a whole lot with it until we actually get to writing SQL in chapter 7. But once we know how to write the SQL commands, we're not really going to say, oh, hey, let's do the relational algebra. We're just going to write the SQL instead. So we need to go over it. We need to talk about it here. But again, mostly we're going to take this at a high level and just know you can go look these things up again if you need to. So a lot of definitions here, right? For a given, minimal implementation of a relational database management system, you need to be able to select, you need to be able to project, and you need to be able to join. Join is the cool one. This is where all the magic happens. And select and project we'll get to in a minute, but it's essentially a mathematical principle of how we manipulate our relational tables. So there's a couple other ones we're going to look at as well. We'll look at intersect. We're going to look at union. We're going to look at difference. And we're going to look at product. And we're going to look at divide. That's a B, not a D. Divide. I can spell. Divide. Right? So we're going to look at what all of these things are. Again, the idea here is that we are implementing these against a table or a relation, the big R relation here. So we're going to look at how these work. Right? So what we get with a select here. So the idea with the select is we're saying this is our restriction view of a given table. And now you can just say, hey, I want to select all. So select all, fine, or select star is pretty common here, right? We'll just give you everything out of a table. So if my original table had a bunch of columns and rows, I'm going to get all of them back out. But what gets interesting here is you can add some restrictions to it. So if I was looking at, say, the student table, I could say, hey, select only where GPA greater than or equal to 3.0. So we can start throwing some math in, right? Some relation operators here. If it's greater than or equal to, you could say if it's less than, you could say if it's equal to, any sort of option here. So we're going to select only where the GPA is greater than 3.0. Right? Or maybe we want to say, hey, I want to select only where ID is equal to 1, 2, 3. We'll find student number 1, 2, 3. So select, it can be for everything, but a lot of times, often we'll have a restriction in here as well. So that's our restriction. Now the relational algebra for this, the notation is the Greek sigma. I have no idea. I didn't come up with it. I'm sorry. But we say sigma, and then maybe we'll say GPA greater than or equal to 3.0 of the student table. Right, so this is the table, this is my restriction, this is the select. Right? So our restriction here gets thrown in here. This is the name of the table. And this is the select operator. So that's the select. That's how we would write a select or restrict. The idea here, one of our technical terms, is that you have closure. That's a property of our operator. It means that we essentially create a new table or a new relation with the result. So when we select, hey, where GPA greater than 3.0, we're getting a subset, but that's a new relation that then we can do other cool things on. So select, again, we were going to get this horizontal view. Right, we're going to get all the rows that match, right? All rows that match. Here. Now, separate from that, right, a different operator here is project. Project lets us get just the columns that we care about. Columns are attributes, right? The columns are attributes. So you can project on a given relation or table and say, hey, I only care about first name and last name. Right? Maybe that's all I want to get out of the student table. And the technical, or the term that we use, the Greek letter, I don't know why these are all Greek letters, we use pi, P for project. So project first name, last name from student. So that I'd get a list, another relation of all of the first and last names out of the student table. Now again, this all by itself is not really all that interesting. But what we can start to do is we can start to combine these. So if I just want, like, hey, I'm going to send out a bunch of letters to people who made the dean's list, I can say, hey, I want to select where GPA greater than or equal to 3.0 from student. From that result, I want to project, well, I'm just going to say name. Like, it'd be first name and last name, sure, name and address. So I can project from the result of a select. So I'm going to say, okay, just give me the columns of the attributes that I care about where this given restriction applies. Now I can have a nice little mailing list. I have your name and I have your address, and I can send you a nice little card that says, congratulations on making the dean's list. That sort of thing. So we generally will combine a select and a project. Right. Another operation here we can do is union. So union is about joining tables together, and maybe not even full tables. Maybe we're going to join partial tables, like those results of other operations here. Right. So if I were going to go maybe say, hey, we're going to put together a mailing list to send out to all of our staff and all of our students and all of our faculty because we want you to contribute to the Student Scholarship Fund. Right. I could union here the result of a bunch of different selects and projects. Right. So I'm going to say, hey, I want to select from student. I want everything, so there's no restriction here, right? This is just all, essentially, right? I'm selecting all, and I want to project, right, name and address. And then I want to union that. So the union notation here is just a big old U. This one's pretty nice here. It's actually a funky character. It's not really the letter U, but it looks like the letter U to me. So I always imagine it's a U here. It's a little bit wider and squatter, maybe. That's union. Right, so we're going to union that with a project, name and address from a select of, we'll say, faculty. Right? And then again, we could union that, right? We just keep on going here. Union that. Oh my goodness, what happened there with that notation? No, erase. Right? We would union that result together with a project of the name and address of a select, and again, all from staff. Now, what's cool about union is it's actually going to combine the common rows. So if you're a member of the faculty and you're also a student, like I'm actually in the student database. I took classes at OCC years and years ago, and actually recently, as part of the prereqs for my doctoral program, I came back and sat on the other side of the classroom. Gives me another appreciation for you fine folks and what you're going through. I'd be in both lists, so when we union those results, we're going to get just the single entry for each of them here. Right? We're not going to get a bunch of duplicates. So this will be all the students, all the faculty, all the staff, all in one big result. Now, the opposite of a union here is an intersect. So where a union puts them all together to give you all the results, the intersect, oh my goodness, that's terrible handwriting. I'm sorry, let me try that again. Just got to lift up the pen. Intersect. There we go. If I lift up the pen, it works a little better here. So intersect is only rows that exist on both relations. Again, so if I did that faculty and student, right, maybe I wanted to say intersect, so I would take a select of student, and again, it probably project the name Sure, we'll just project the name here. I want to intersect. So intersect is an opposite of union. So it's the like a big old N looking hoop here. And that's the intersect. Intersect on the projection of name from a select of faculty. Okay, so the intersect would give me just the ones that are in both of those relations here. We can get an intersect. So that's kind of handy. And actually, it's I don't know how common it is, but some faculty like to take other classes just to learn other things. Because generally, if you get into teaching, it's because you love learning and you think that sort of thing is fun. So you might be interested in other things, and you can take other classes for fun. I'm actually hoping to go back and take some more math classes. Math is super fun for me. All right, the next one here is the difference. So difference, right, that's our notation here, is just a minus sign, which is nice, is what is in the left that is not in the right. Right, so what's the difference here? So I'm going to say, hey, maybe we want to look at all students who are not faculty. So again, we would project name from a select student. And then we want the difference of project name from select of faculty. Gotta lift the pen. I'm sorry. I'm getting it there. Right. So it's going to say all of the students who are not on the list of faculty. So what's on the left that is not in the right. So this would give me only students here. Right. So it's essentially it's taking the intersection out of the left side, right? It's doing the intersect, finding what is the between them here, and removing them from that. Okay, that's essentially what's happening there. Right, so those ones are relatively straightforward. Again, lots of crazy notation. Don't worry about memorizing any of it. You can always go look it up here. And now product, it's a little silly here. So product is every row with times every other row of the other table. So if I had, I don't know, maybe it would make more sense if we had like a course and a student table. So if I said student times course, I would get every student, so like student 1, student 2, student 3, Bob, Mary, Tim, yada, yada, yada. And for each one of those, I would get every course. I'd get 1200, 1500, 2151, on and on and on. So every instant, every row is combined with every other row of the other table. So if you have, say, 10 students and you had 5 courses, you're going to get now 50 rows here. You'll have each student with each of the 5 courses listed. That doesn't seem very useful. And actually, it's not all by itself. We're going to do something with it in a minute here. And our notation for it is the X sign. That's our multiplication sign. Right? That's for product. Again, all by itself, not very interesting. It's known as a Cartesian product. That's our technical term. Cartesian product. Okay, not all that interesting. But again, we'll get to it in a little bit here. What is more interesting here is talking about joins. Now, joins are where the real power of relational databases are. So a join says, take this table and join it to the other table. How? Well, where we have a matching foreign key, primary key. Right? So if we said, hey, I want to find all of the customers, and I want to join on my sales table, I'm going to get all of the customer fields. So I'm going to get all the customer information, customer, name, phone number, address, yada, yada, yada here. And then I'm going to get the salesperson's ID, right? So then the sales ID, name, whatever, office number, something or other. I'm going to get all that information. Generally, we'll call that a natural join. So how that works, though, is a really cool process. What it does is it creates the product of customer times sales. Right? We get every single customer and every single salesperson listed out. So for every customer, we get every single salesperson. So we're going to get a large result here with the join. right? Then we're going to select from them where the sales ID in customer, right? So customer sales ID is equal to the sales table ID field, right? So we do the Cartesian product, and then we are going to restrict that, selecting just where those match, right, of this result. So actually all of this should get, let's see, can I move that? I think I can, no, I can't grab it all. Right, so it would be a select of, this is the restriction here, right? The select of customer times sales. Okay, so we would do that restriction here, right? Our little select result. Come on, there's the eraser. Good. And again, we're going to join where that sales ID matches the ID in the other table. So where the foreign key, right? My foreign key matches the primary key. Then we do a project from here to remove the duplicate columns. So I don't need sales ID and the sales table ID fields. I'm only going to project all of the unique fields here. Project all non-duplicate fields. Okay, so that's our join. Now, what you're not going to get, right, is if you have a salesperson who just started, who hasn't been assigned to any customers, they're not going to be in the result because they had no matches here. Right? This restriction took them off the list. Or if we had a customer with a null for salesperson ID, null's not going to match anything. They won't be on that list either. So again, that's another reason why nulls can be a little bit tricky here. We have to be a little bit careful if we're using this sort of information. Now, typically, we would use the join notation. We'd say, hey, sales, or we'll start with customer, right? And we're saying customer join. So the join is this little like X with the lines here, kind of on either side, almost like, do that better here. X. Right, that's our join. So customer join sales here. Now, we don't actually, again, do that directly, but it's really a big pain to write out this big customer times sales, restrict on, select on where they match, project these other fields here, right? That's a lot to write. So typically this is our shorthand notation for that. But what it's actually doing behind the scenes is all of that other operations, which is cool. So that's our natural join. A couple other kinds of joins. You can have an equality join or equijoin, where you could say like greater than or less than, and that you're not actually basing off of a primary key. That's some other sort of comparison. Those are really funky. We're not going to use them really. That's okay. So if it's not the equals operator here, right, it's a theta join. So some other joins, again, don't worry too much about the terms. The big difference here, though, these ones are important, are the inner join versus an outer join. So an inner join was the natural join that we're looking at. Right? We're only going to get matches. Matches only. Right? That's our natural join or equal join, right? Where this one matches here. Okay? We're probably not going to do those theta joins with greater than less than. Those are going to be really funky. So, but the inner joins are the matches only. The difference with an outer join is you get all of one table, regardless of if there are matches or not. So, and you can pick a left outer join, or you can pick a right outer join. So if I say customer, and I want to left outer join, join sales, I'm going to get all customers regardless of if there's a match with sales or not. So then in that case, I'm going to get all customers, maybe even if they have null for an agent. Right? So again, if that's what your business case is, you need to be aware of how that's going to work. Right? For our results here, a customer, right? So this is all customers, regardless of if they have a match. A customer right outer join on sales will give me all the sales, no matter if they have an assigned customer or not. So again, you get all of the right table or all of the left table with the join. Now, I'm not fond of right outer joins. I find they're awkward, and really you could just write it the opposite way. If you wanted this, you could just say sales left outer join customer, right? And that's going to do the exact same thing. So right is sales here, left is sales here. Left is just more common. Usually if you're going to do an outer join, it's a left outer join. It's just sort of a convention. All right. So again, lots of funky terminology when it comes to relational algebra. It's important to know that it exists, but don't worry too much about it. It's not that big of a deal. Again, we'll look at when we get to SQL commands how they essentially are doing this relational algebra. All this stuff happens behind the scenes. If you're taking a specific like database technology course, how you actually implement these at the database level is really important, and you can get into the theory of all that. Super interesting, lots of really cool technical stuff that makes databases work really nicely. But again, it's a lot of theory. The last operation we're going to look at then is divide. Now, divide is going to say, hey, give me only where there's matches here. So if I have a list of, say, customers and products that they bought, and I divide by the products, I'm going to get the result of customers who bought those products. Again, divide's kind of a funny special case here, but we can say, hey, I want to take this relation and divide it by another here. Right, so we're trying to find where are there matches? Where is there this information between the two with our divide? So you would probably have some other sort of list, right? So again, our like division symbol is our operator here. So we're not going to say like customer divided by product, because we need a list of customers and products to see who they bought. So there's some other relational algebra happening to give me that list of products and customers, and I can divide by a list of products, and it's going to find every entry that has that product number. Right? If it matches, I'll get out the customer. Right? So product, and this was customer. I'll get out just the list of customers. Okay, so that's the last operation there. Again, real heavy, a lot to it. It's some really interesting theoretical stuff. Just know there's different operations, and we can go look them up, and we'll figure out how we map all of these in SQL later on.